Welcome to Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public. With that in mind, every week we introduce you to a scientist working in the field of materials and nanoscience. Hi everyone. Today we have with us Andrew Princep, who is a Keeley Rutherford Junior Research Fellow at the Oxford University. Hi Andrew, how are you doing?
I'm doing great, thank you. How are you?
Good. Looking forward to speaking with you and understanding your research even more in detail. So let's begin. Let's start with how did you end up in your current research field?
So the way I ended up here was basically pure chance. I did my undergraduate research in nanotechnology, or my undergraduate degree in nanotechnology. But I was always really fascinated by crystals and crystallography. And then my third year electromagnetism researcher, I really liked her, and she offered me a summer research project. Which was basically on X-ray scattering. And then she offered me a master's project in neutron scattering. And I then did my PhD with her in X-ray and neutron scattering. And that was all to do with magnetism and rare earth crystals. So that's basically how I ended up as a condensed matter physicist.
Okay, that's really interesting. So, where does your current research fall in this big picture of materials and nanoscience?
So I think being a condensed matter physicist basically makes me a material scientist who's really interested in the fundamentals. So generally speaking, I want to know not what something does, but really why and how I can play with that to make it do something maybe a little bit different, or what are the limits of how you can change a material before it does something completely different. And so this leads us to be, or people like me, to be really interested in properties like magnetism and superconductivity, especially since these tend to eventually lead to very useful devices.
Okay, all right. That's really interesting, actually. That's awesome. So it sounds to me that you must be doing a lot of interesting experiments and working on a lot of different research projects. If you had to pick one that you're proud of or the most exciting and interesting one, could you pick one experiment or project and explain it to us in simple words?
Okay, so I certainly hope I can. The piece of work that I'm probably the most proud of was I published what is the most complete measurements of the magnetic properties of a material called yttrium iron garnet. So we used a lot of neutron scattering data for this, and this is a material which has been really widespread in its use in industry for a long time, but it's also now the basis for an entirely new type of technology, where you basically try and perform computing using only like really subtle magnetic effects in the material, which so it ends up being completely different and much lower energy consumption than regular computing. We showed, based on our measurements, that some important symmetry information about this material had been missed before. And this led to basically a sort of change in the understanding of what interactions are important and what drives the magnetic properties of this material that make it so useful. And we also confirmed some computer-based predictions showing that actually you need to include very long-range interactions, which is a bit unusual in something which is based on iron. We were also able to produce a model that can be used for very accurate simulations in the future, and we're actually working on doing some of those simulations ourselves.
Okay, so was it purely theoretical or was it complemented by the experimental work as well?
So my contribution was almost entirely experimental, but there was a lot of computer modeling that went along with that because the data that you get is four-dimensional. So you need quite some help visualizing this and then fitting a model to it. And I think the model that we ended up getting has such beautiful agreement with the data. It makes me happy every time I look at those figures.
I personally love it when there is like a very good combination of theoretical and experimental work. And as you said, if the model fits beautifully, it's like the best thing ever,
Yeah.
right? Like theoretically, this has been predicted, and experimentally, this is exactly what we found, or very close to what the theory says. So that's always nice, right?
Yeah.
Okay. Well, I can understand why you picked this as your favorite or most proud experiment. I can understand that. Okay, wonderful. So, do you also teach, or is it mainly the research position that you have?
So I do quite a lot of teaching as part of my position. So I teach to second years thermodynamics and statistical mechanics,
Mm-hmm.
and to third years I teach condensed matter physics.
Okay.
And because I'm at Oxford, I am also involved in the interviews that we do for prospective undergraduates,
Okay.
which we've just finished this week. So I interviewed 30 students in 3 days. It
Oh
was
my.
like so many hours. I was so exhausted.
Okay. So, do you have like a certain set of questions, or do you just go spontaneous with the questions for people who might be interested in attending Oxford as an undergrad student?
So we try and change the questions every so often because we are aware that some people memorize the questions and then will like post it on online forums or like tell their schools and that kind of thing. But it's also very important that every interview is quite consistent. So we do ask every candidate the exact same set of questions, basically. I mean, time permitting, of course.
Okay, all right. And about the courses that you mentioned, so you teach thermodynamics and statistical physics and condensed matter physics.
Yeah.
And thermodynamics and statistical is for grad student or undergrad students then?
Second year undergraduates, yeah.
Second year undergraduates. Okay, and the condensed matter physics is also for undergrads then?
Yeah, so I do also teach the master's level version of that.
Okay, all right. So which is your favorite? Which one do you like?
I think I like the third year condensed matter physics the most because it's obviously very special to my heart, that particular topic. And
Right.
it's always fun teaching people all the like many little tricks and subtleties that you've learned over the years.
Ah, nice. And when you're teaching, do you do more like, are you more of a chalk and board kind of a lecturer or more like slides or more, what's your style?
So I don't get to lecture, although whenever I do deliver some sort of presentation like that, I am very much a slides person. I hate chalk and talk. I don't know why. It's just ingrained into me. But I love slides, especially because slides I can fill with like memes and pictures and like I feel it's very important to strongly visually engage with your audience.
Okay, yeah, that's also important for Twitter. So
Yeah.
you're gonna have so much fun with you with you curating the real Sana on a Twitter account. Okay, wonderful. That's really nice. Let's move to a bit of the research experience. Let's talk a bit about your research experience. I hope it has been wonderful so far, and it will continue to be wonderful in the future as well. However, if you had three wishes to improve it, what would you ask for? And I'm not promising anything here.
No.
So.
I think my three wishes would definitely be a permanent job, uh, more funding, and someone whose whole life was growing samples for me, because this is always the big sticking point for my research. Those crystals do not grow themselves, and it's very challenging.
They're special from batch to batch, huh?
Yeah. Well,
Producibility.
sometimes too special. You get one batch and it does exactly what you think it should, and you get another batch and it just behaves like some other different material, and you just cannot understand why.
Yeah. So, do you grow your own crystals then, or do you collaborate with other groups who are growing?
I only grow my own crystals if it is really easy, because I am not good at that. So generally, it involves collaborating with quite a few different groups because it's a hugely time-consuming process. So if two or three different people are growing different things for me at the same time, then I can keep up a steady supply of experiments.
Uh-huh. Okay, so there's a community of growers.
Yeah.
It would be interesting to get them on Real Nano as well to talk about the growing, the difficulties and the challenges that they're facing. Yeah. That sounds good. Yeah, well, all three of your wishes are really important, I feel, and I agree with you on the funding, the
Yeah.
job situation, the duration of the job situation, and the needing the growers. I think they are very important.
Yeah.
And I wish I could grant all those wishes with a snap of my fingers, but I can't. However, I hope we are working towards it, at least with the first two, which is the funding and the permanent jobs. I hope we are working towards it. Hopefully, 2020 would see some changes. Hopefully, yeah. Speaking of future and 2020, what are you most looking forward to in the next 3 months?
So in the next 3 months, I think the two things that I'm most looking forward to are the LGBT seminar, because this is always like a really positive and friendly experience.
Mm-hmm.
And I'm probably also going to go to the American Physical Society conference in Colorado in the US.
Okay.
The meeting in March, which is, I guess, just inside 3 months.
Yes.
And I'm also hoping to publish some follow-up work on my yttrium ion garnet stuff.
Okay. Well, sounds cool. Sounds very good. And we are excited to hear and read about the LGBT seminar on the Friday, the 14th, or something like that. Yeah.
Yeah.
Yeah, 14th. Yeah. Okay, wonderful. Before we let you go, we would like to understand from you the challenges or the big questions that the materials or nanoscientists are working towards solving or are facing.
Yeah, okay. So in the sort of area that I work on, the challenge is basically boils down to finding newer and more efficient materials to replace the things that we already use. Um, Particularly in the face of things like limitation of resources. So batteries are often based on lithium, so we would love to be able to replace lithium, which is a very rare element and it's quite expensive.
Right.
Climate change and the sort of increasing use of computation or like devices with computers that control why they do things, or just generally the more like expansion of devices that consume power. We have a huge increase in a need for power and also for computation that's efficient. And
Mhm.
so we both need a better means to produce energy, we need a better means to distribute and store energy, and we also need to be more efficient about how we use energy, especially when it comes to computing.
Okay. All right. That's quite exciting to solve all these challenges, and I hope we solve them in 2020. Probably too optimistic, but let's hope. It's always good to be positive. All right. Thank you very much, Andrew, for speaking with us, and we are excited to have you on Real Scientist Nano.
Thank you very much. I'm excited to be there.
Thank you for listening. To know more about us, please visit our website realscientistsnano.org and follow us on Twitter at realsci_nano.